Welcome back to the final session of CS 520. In this session I'm going to talk about two historical machines. The first one was one of the very first machines built, what I'm going to refer to as the IAS computer. This discussion is based upon the 1946 report by Birks, Goldstein, and von Neumann. That's linked to the course webpage. I'm calling this the IAS computer because it was designed at the Institute for Advanced Studies at Princeton University. So this is an ancient machine. So right off the bat, the first thing we notice that it only has 4K words in memory, and those words are 40 bits, however. So again, as you would expect in the early days, they were primarily interested in computation. They weren't thinking about shuffling bytes around like we do today. So relatively speaking, big words, 40-bit words. Machine only had 3 registers, a program counter, because of course, since von Neumann was involved, it was a stored program computer, so it was fetching instructions out of memory, and the program counter, as in modern days, kept track of where the next instruction was. It had an accumulator register, which was the primary register, and then for multiply and divide instructions, it had a second register, the MQ register, which you could use to capture the full 80-bit output of a multiply, or you could capture the division result as well as the remainder through the accumulator and the MQ register. Had a small instruction set, and consequently they didn't want to use a full 40 bits to encode instructions, so they packed 2 instructions per word, so 2 20-bit instructions per word. With the 4K memory space, it required a 12-bit address, and it left 8 bits for opcodes to be specified. So we would call this a one-address machine because it used one-address instructions. There was a single address in the instruction. How could this work? Well, it worked because the AC register was implicit. So a load instruction, for instance, we did not need to say where the load was going to put its result. The result always was the AC register, and similarly for the arithmetic instructions, you're operating on a memory address and the accumulator. The 1946 report describes the 40-bit values as being fixed point. The leftmost bit is a sign bit, but the radix point was assumed to be right before the next bit moving to the right. So a 40-bit value that contained a 0 and a bunch of 1s like this represented in the programmer's mind a positive number with the decimal point here on the left and all these digits stringing out to the right. So very much like a modern integer, but with the radix point at the other end. Right? In modern days, we think of integers as having the radix point immediately to the right of all the bits. But very similar to our concept of a modern integer. And in fact, this machine used 2's complement for negative values, just like we see on modern machines. If you look into the 46 report, you'll see a discussion, however, of floating point. The designers explicitly rejected floating point. It wasn't like they didn't know about it. It was something they considered, but it was rejected as it would, in their opinion, it would have complicated the design of the CPU too much. By the way, they don't use the word CPU; they use control. So what this meant with these fixed point values is for each value the programmer would maintain a scale factor, sort of similar to the modern exponent that we see in floating point values, but of course not necessarily a power of 2. And again, if you look at that 46 report, you'll see that the designers basically said that floating point was better maintained in software than implemented in the hardware, given the building blocks they were working with at the time. That was probably a wise decision, I guess. As I said, it was a relatively small set of instructions. You basically had these, you could load and store, you could do arithmetic operations, including negate, you could do left and right shifts. You had branching instructions, both conditional and unconditional. You could move values between the two registers, the two data registers, AC and MQ. And then at the bottom of the list here, I've put the most provocative one. The real reason I like to talk about this machine is it had an address modification instruction. And you're probably sitting out there wondering what the heck is this? Although I may have mentioned this earlier in this semester. This is one of my favorite things to talk about. But this instruction changed the address field of another instruction in memory using bits from the accumulator. Okay, so it explicitly was an instruction to change the bits that were encoding another instruction. And this was included as a way to do array indexing. So you'd write a loop to loop over an array, access all the values in the array, and inside the loop would be one instruction to modify a load instruction in the loop, so that every iteration you would advance to the next array element by updating the address field of the instruction that referenced the array. So to me it's just amazing. It's self-modifying code with a vengeance, sort of extreme self-modifying code, and I guess the complexity of implementing instructions led them to this. They needed some way to do array indexing, so they did it by modifying the program itself, because again, that's the advantage of a stored program computer. You've got the program as data sitting in memory, so why not? Let's go ahead and change it on the fly. Okay. Well, sort of routine self-modifying code lived on for many years. So again, going back to the machine that I've mentioned several times in this semester, the machine I was brought up on, so to speak, the CDC 6600, again a mid-60s, a mid-1960s design. It had an instruction called the return jump instruction, and it used this to do function calls. So if we look into a program here, these are the addresses of the instructions, and these are the instructions lying at that address. So if a programmer wanted to call a function, they would do an RJ. If the function entry point was at address 201, they would do an RJ to address 200. And what the RJ instruction did was it stored a jump to 101 into that location 200. So the RJ 200 instruction would, look at the PC essentially, see that it was 100, update it to be, increment that to 101, and then store a jump instruction in here to 101. In other words, it would store a jump to the return address at the location 200. It would then fall in and execute 201 and start the body of the function. When the function wanted to return, then what would it do? It would do a jump to 200, which then had a jump to 101. So again, it was self-modifying code. We were dropping in encoded instructions into memory addresses and then executing them. Of course, if you think about this for a minute, this is not going to work for recursion, right? Because I can only have one copy of this function executing at a time, because there's only one place to put the return address. All right, so the CDC machine did not have direct support for recursion. And as we've studied at length in this course, modern machines have runtime stacks for this purpose. Okay. Well, other CDC 6600 fun facts. Some of these I've mentioned before, but let me just point them out one more time. The machine had a memory of 60-bit words. So again, the machine was, even in the 60s, it was still there primarily to compute floating point. They weren't worried about moving bytes around very much. So 60-bit words, again, as I think I probably mentioned earlier, ones complement integers. Seems strange by modern standards because there's just two zeros. If you go back and think about ones complement. And it had a proprietary floating point, which of course was not unusual for the era, but it did have floating point. Again, it had a relatively short list of instructions. It certainly wasn't going to use a full 60 bits to encode instructions. So it had, like the IAS machine, it had multiple instructions packed per word. I didn't talk about this, but this complicates the program counter, of course, because not only are you going from address to address, but you're going from offset to offset within an address, because there's multiple instructions per word. So for instance, the address modification instruction in the IAS machine, there was two versions of it, one to modify the left instruction in a word and one to modify the right instruction in the word. Okay. And since you could only branch to an address, you also had to often do things like pad out your instructions, so that things were on an even word boundary when you wanted to branch there. All right, one other thing that I'm sure I mentioned before, but let me just bring it up again. The 6-bit, this machine had a 6-bit character set, proprietary character set, so it only had lowercase letters, had the space in the wrong spot relative to the letters, so it was not a fun machine to do any kind of character processing. It wasn't designed for that purpose. But the CD machine was a modern machine in many respects. For instance, it had internal parallelism. The CPU itself, if you opened it up, it had multiple functional units, so it could be computing multiple instructions at the same time. It had multiple memory banks, so it could be reading multiple memory locations at the same time. Again, these are things you find on modern machines to try to address the ever-increasing need for speed and the fact that memory is slow relative to the CPUs. Also, it had a load-store architecture to allow instructions to be overlapped, so you could load the next operand while you're computing the last instruction. Again, these are all techniques that you see in modern machines. Okay, that's where I want to end. I just wanted to give you some basic facts, in particular to point you at that address modification instruction that was in von Neumann's original machine, which I find very interesting. If you read von Neumann's papers, you'll see he foresaw lots of things. Like there's a discussion of linking in one of those early papers, for instance. He was already thinking about, manipulating pieces of programs, connecting them together. It's really quite amazing, his vision. He and his co-designers. Okay. So let's stop here.